MATLAB has a variety of functions that are specific to polynomials. MATLAB will integrate, differentiate, multiply, divide, and find roots of polynomials, among other things. In this video, I'll give a brief overview of some of these commands, and then talk about what's important to this chapter, MATLAB's built-in function for curve fitting using polynomials. Polynomials are equations of this form. The value of the polynomial is the sum of terms that individually are powers of the independent variable x, multiplied by some numbers. The powers are all non-negative integers. So y of x is equal to some coefficient, a number, times x to the n, plus another coefficient times x to the n minus 1, and so on down to x to the 0th. The degree of the polynomial is the highest power of x, so this is an nth order polynomial. Here are a few examples. Y of x here is a second order polynomial, which is also called a quadratic function. This polynomial is fourth order. Notice that it doesn't have terms corresponding to x squared or x to the 0th power. This means that the coefficients multiplying those particular powers of x are 0. This is a first order polynomial, which is just the equation for a straight line. This one has a slope of 2 and a y-intercept of 1. To specify a polynomial in MATLAB, just place the coefficients in a row vector with the coefficients listed in decreasing powers of x. The last term will always be the x to the 0th power term. For example, the coefficients of this polynomial in decreasing order are 7, -2, and 1. So my vector defining the polynomial is just 7, -2, and 1. The rightmost term will always be the coefficient of x to the 0th power. This polynomial has coefficients that are 0 for the x squared and constant term, since there's no x squared or constant term in the equation. So the coefficients are 5, 2, 0, -1, and 0. The zeros are required as placeholders so that MATLAB can keep track of what power of x corresponds to the non-zero terms. The equation for a straight line, which is a first order polynomial, has only two terms. The slope is first and the y-intercept is second. Now I'll give just a quick list of some MATLAB commands that use polynomials. For the most part, I won't tell you the syntax for these, since you can use MATLAB's documentation to figure out how to use them once you know the function names. Polyval evaluates a polynomial at some point x. Polyint integrates polynomials. Polydir will take the derivative of a polynomial. Roots returns the roots of a polynomial. CONV is the product of two polynomials. And DCONV is the quotient of two polynomials. Finally, polyfit performs least squares curve fitting of polynomials to data. Now let's talk about polynomial functions that are useful for curve fitting. The polyval function determines the value of a polynomial at a specific value of the independent variable. The syntax is y is equal to polyval of p comma x, where p is a vector containing the polynomial coefficients and x is an array containing the values of the independent variable. The function returns an array y, which corresponds to the values of the polynomial at the values given in the array x. The polyfit function does a least squares curve fit of an arbitrary order polynomial to a set of xy data. The syntax is polyfit of x, comma, y, comma, n. The x and y vectors contain the x and y values of the data points, and n is the order of the polynomial to be fit to the data. A vector p is returned, which contains the coefficients of the polynomial. Next, I'll do an example of how to fit a straight line to some data and display the original data along with the curve fit. These are my vectors of data points. I can curve a straight line using the polyfit command on the x and y data and specifying that I want a first order polynomial. This results in exactly the same process I did in the previous video by solving a system of overdetermined equations. Since I'll want to display the line approximating the data, I'll evaluate some points on the line with the polyval command. So in this command, I'm calculating points on my straight line using the polynomial coefficients from the previous command and calculating values at the same values of x as my original data. Finally, I'll plot the data and the curve fit. Now I'll go to MATLAB and walk through this process. After that, I'll demonstrate what happens as we fit higher order polynomials to some data by changing this argument in the polyfit command. I'll start out by implementing the code exactly as I outlined on the slide. The data is defined, and I use the polyfit command to create a least squares best fit straight line by specifying a first order polynomial. Then I create a line based on the curve fit and plot the line and the data points together. Looks like a reasonably good fit, but let's try increasing the order of the polynomial used to fit the data. When I use higher order polynomials, I'm going to add a few values to the data set I'm using to fit the line. Here are my new x and y vectors. They contain the same points as before, but include a few extra ones too. The line still looks like a pretty good approximation. Now I'll do the same thing, but with a quadratic. The last argument to the polyfit command is now a 2, and my polynomial coefficients are now returned to a vector named p2. I'm also going to set up a different vector of values where I'm calculating my curve fit to include a lot more values of x. It didn't matter when I was using straight lines, but since I'm now using a curved line, I want to be able to see its shape between the data points better. Finally, I calculate the values of y at these x values and plot the data with the curve fit. That looks like it might be a better fit to the data, so it seems like higher order polynomials are better. In that case, let's go to the extreme. This code does a 10th order curve fit. It's the highest we can go with 11 data points. This curve fit is great at the data points. It passes through all the points and the curve fit matches the data exactly. However, I'm pretty sure that the process I'm measuring doesn't have these large wiggles in whatever behavior it displays. So I would really not want to use this curve to predict what would actually be the value for y at an x value of, for example, 0.05. The problem actually gets worse if I try to predict what the data would look like outside the range of x values that I measured. Let's see what the curve fit looks like over a range of minus 0.02 to 1.02. I'm only extending the range of the curve fit by 0.02 beyond the range of the data covers. The curve fit just completely goes crazy outside the range specified by the data, and I can't believe it at all. So here are a couple practical points about curve fitting. If you use a polynomial curve fit, it's usually best to use the lowest order polynomial that you think adequately represents the data. Even better, use some physical insight into the system itself to decide what kind of curve to fit to the data. Quite often, the governing equations for the system indicate what type of curve you should use, and then the curve fit can help you decide what the coefficients in the equation are. Now we can fit lines to data using MATLAB matrix operators applied to overdetermined equations, and we can streamline that process by using MATLAB's polyfit function. But what if we need to fit a curve to data that's not a polynomial? There are some tricks we can do with our existing tools to fit non-polynomial functions to data. Those are the topic of the next video.